Thanks everyone for coming to my talk. My name is Michael Bironneau. I work at a company called Energi. I'm going to tell you a bit about us in a minute. But today what I'd like to cover is some very specific use cases that we have for Apache Nifi, sort of combining the IoT, streaming technology, and machine learning all in one. So first of all, I want to talk a bit about the company and the kinds of problems that we address. So if I take you back about 1 century to the first power station was ever built, so this was built by the Edison Corporation, it was only utilized about 25% of the time. Part of the reason is simply that at the time there was not as much demand. But you would think that now with a lot more demand for energy, a lot more experience in optimizing energy systems, in fact, we would have got a lot better at optimizing that utilization. And in fact, that's not true. If you look across the generation fleet, so this is the UK because we're based in the UK, utilization is barely above 25% now. And you have to ask yourself, well, why is that the case? Because you have really smart people working on this. And part of the reason is demand is really, really, really hard to forecast, and it's hard to control. And the other reason is, well, if you think demand is hard to forecast, try forecasting wind generation in Scotland. That's equally hard. And if you look across the fleet, the utilization of wind, for example, which is sort of the lighter shaded area in that chart, is a lot less than the utilization in, for example, coal, because it's just part of it is because it's harder to forecast. We come at this from the other side. We don't touch generation. We say, well, actually, hang on. There's all this inherent stored energy in all the assets that we use every day: refrigerators, bitumen tanks, water pumps. And we use all this distributed energy to create essentially what we call a virtual power station to help do that, to help put the grid back in balance. So where in the past we would have had to tell a wind farm not to generate and to be underutilized just because there wasn't enough demand to absorb that power, now we can say, it's okay, we'll absorb that power inside assets that would have consumed it at some point anyway, and we'll keep the grid in balance while doing that. So what does that look like? So we'll connect to all these assets. So on the left-hand side, you have a very long list of them, and that list is actually got longer over the last few months. We'll install some hardware on site, which we call a dynamic demand gateway. It's basically a controller, and it reports data to us, and it can also interface with PLCs and SCADA systems and things like that in order to affect changes. It grids grid frequency, which is essentially a measure of how in balance the grid is at any given time. And it can then process those changes and unlock the flexibility in the assets that it's connected to. So it essentially looks like that. On this site, you'll have all these applications. Then you'll have our panel. It reports everything to us through 3 or 4G connections. And then we'll sort of process that. We'll report on it to National Grid within 30 seconds, which is what we're contracted to do. And we'll also keep some of that data to report to our customers, which is obviously of a lot of interest. If you consider, for example, the water sector, where you have pumps that are maybe like 30 or 40 years old, these are very, very data-poor assets. It's not easy to collect data from them. It's quite an expensive process. The fact that we have a way of actually making money from it means that we also have an excuse to go and collect even more data on those processes because it's useful to us, and then to share that data with the customer because it's useful to them. So, for example, a water company, a freshwater company, might want to know how much energy it takes to produce a hectoliter of water. Well, if you can't measure all the operational processes involved and you can't measure exactly what's consuming what energy, you only have that at a very, very coarse level. But by going in at this level of detail, you can provide a lot more insight. And this is, if you look at a portfolio level, this is essentially our virtual power plant in operation. So the middle line is what's currently being consumed by the portfolio. The lower line is if we deferred power consumption, all the power consumption, what it would be, what the portfolio consumption would be. And the upper line is if we brought forward consumption from assets that aren't consuming power at the moment, what that would do to the portfolio's consumption. So as you can see, a lot of our assets are off a lot of the time, hence why we can increase consumption more than decrease it. And on a more sort of granular scale, this is our portfolio responding to a frequency event. Finally, why do we do this? Well, if you're not building power stations, you're not buying massive batteries, you're just harnessing infrastructure that's already out there, it's a lot cheaper. So now let's get on to the fun part, our data. So we're installed currently at around 400 sites around the UK, and we have about 3,000 assets that report to us from those sites. Roughly speaking, it gives us about 20,000 messages per second. That's not large scale. I don't claim that that's a huge amount of data. However, the interesting bit happens when a lot of those messages report an operational change of state, and that operational change of state means that the flexibility of that asset or the amount of storage available has suddenly changed. For example, if the air conditioning in this room suddenly turns on, well, we can't bring forward any power consumption because it's already on. We can't turn it on anymore. So that, for example, might require us to change our processing, and again, with that sort of low latency requirement so that we can report back to National Grid and say, the energy stored at the moment in our system is slightly less. And all of these messages are going to require some form of aggregation for reporting processes, be it the total consumption of our portfolio, which we have to report on a second-by-second basis, or be it very simply a customer who wants to know exactly what the temperature is of, say, a bitumen tank right now, just to make sure that they don't have an incorrect set point for the tank, which is actually quite an easy thing to do. And before I go into the specific use cases, what kind of drove us to use Apache Nifi as sort of an orchestrator for all this data? Well, the first thing is that if you start with IoT data and you don't really know what you're doing, like, well, we didn't really know a few years back, data provenance becomes a little bit of an issue because you have data coming from a device that goes to a server that's transformed and it's transformed and it's transformed and it lands in a database and an ETL process transforms it again. And by the time you're done with all this, you have 3 different systems with 3 different versions of the same ground truth. And they're not all consistent. And that's not always an issue in the streaming part of your system. That's a wider issue. However, you can certainly make improvements to the way you persist the data, and so that every step along the way is recorded and is fully traceable. And that's one thing that Nifi provides. The second thing, which is really nice, is that when you're dealing with highly distributed communications and really flaky networks, sometimes a phone mast is just going to go down. You're not going to receive any data for a couple hours, and then it's suddenly just going to come piling in, and it's going to overwhelm your systems. So having a mechanism that can deal with back pressure and that can deal with some fault handling and that can do it in a sensible way was definitely a huge requirement for us. Easy to use. That should probably go on top. Just by a quick show of hands, how many of you would consider yourselves data scientists or statisticians or applied scientists? Okay, and how many would consider yourselves more on the engineering, sort of software engineering side? Right, so that pretty much reflects what we're like at Open Energy, sort of like, maybe not 50-50, but that was roughly the split. From my experience, data scientists, as a first step, don't like writing storm topologies. As a first step, it's a lot easier to convince a data scientist who wants to collect a new piece of data, who wants to process that piece of data in a new way. Here's a GUI. You can see everything that's happening to that piece of data. If you make a mistake, you can fix it in a couple seconds, and it'll just readjust, and you can see all the data flowing. It's much, much easier. And to be fair, I'm a mathematician and then a software engineer by background. I kind of prefer the GUI as well. Built-in processors for Azure services, that was more nice to have because Nifi is very extensible, so we could have built our own, but it's kind of a nice bonus that it's plug and play with our cloud provider. Easy to extend. Performance, well, like I said before, we don't have an enormous amount of data, so most systems would have probably done the job, but it's kind of nice to know that if tomorrow we suddenly start targeting the domestic market, for instance, and our data goes up a couple orders of magnitude in scale, this will scale with us. Downsides, well, we had a few issues. Maybe I wouldn't call these downsides, that's maybe a harsh term, but the source controlling flows I found to be a little difficult because if you make a big change to a flow, the diff in source control doesn't look as nice. We kind of played around with sort of visualizing the XML so you can see what blocks changed in the diffs, but yeah, it's still not great. And the CI remains a bit difficult. I know there's a proposal on the Apache page, and I'm really looking forward to that. Script components, my recommendation is now don't use them because they're really hard to maintain. And not all processors working in clustered mode. If you use the get event hub processor, beware, because you'll process your data once for every node in your cluster. So now I'd like to jump into some really specific use cases. So I don't know how many of you went to the Nifi sessions earlier today, but they were sort of broad. They were discussing very broad use cases, and I want to show you some very specific things that we're doing. And this is the first one. So on the left-hand side, you have the power consumption of an asset over a period of time since we send it a request. So we can dispatch assets to ask them, for instance, to increase or decrease their power consumption. So at time 0, there's a request. And then after that, we need to measure what's called the response of the asset, which is basically the difference in power consumption from that baseline at time 0, because we need to report that to the national grid. And we also need to measure how long that request lasts, because we need to report that to the customer, because they want to know that we're not overutilizing certain assets, or that whatever switches we do are within the time constraints that we're contracted to do. So if you imagine that sort of this data arrives in a streaming fashion, sort of one point by one point, what we're looking for is to be able to compute a differential between each point and some reference, which might have been cached somewhere, or on the right-hand side, to compute the distance and time between two events. It's not as simple as it looks, because they might arrive out of order. They might not arrive for a few hours. When they do arrive, the baseline point, for instance, might arrive 2 hours late. It very rarely happens, but it has happened once or twice that our comms providers have just had a big issue with their firewall, and some of the messages get held up. We get them later. So I thought I'd sort of flatten out. I mean, this is not nice looking stuff, but I thought I'd flatten out what our initial approach to this was. And Nifi, which looks a lot nicer now, but if you sort of put it all into one flow, flatten it out, and try and do everything in Nifi, which was our first approach, don't use anything else, just use Nifi, you get something like that. And the box at the top is just about extracting a bunch of properties. Then it's about caching basically the baseline, and then looking various metadata up to figure out what the entity is that sent you the data. And then finally, you have those two things at the bottom over here, which are scripting components, and they're literally just little Python scripts to do the calculation. This is when we figured out that it might not be so easy to troubleshoot stuff when you put all the logic into scripting components. But it did the job, and it took us something like half an hour to make the first time around, which is it's quite amazing. I don't know if any of you use Storm or Flink or any of those frameworks. The first time you make something, it takes you a lot more than half an hour to get it running. And this is sort of the second use case, which is more interesting and a more recent one for us after we sort of got the initial hello world type example that I just mentioned out of the way. So the thing that we're really interested in is being able to predict what our portfolio will do if we send it a certain pattern of dispatches. So if we say right now, suppose that we think that in a couple minutes there's going to be some sort of frequency event, what would our portfolio do if we sent this signal, and then we sent another signal? Because if you know what the portfolio is going to do, and you can do this forecasting reliably, then maybe you can optimize for usage. Maybe you can figure out which assets not to use or which assets to use, and you can do this at a portfolio level instead of relying on a very fine-grained and local optimization. So the thing that we're trying to do is, so if at time, whatever that is, 22, 23 seconds from now, we want to dispatch a request, and we have all this data to say, so this is the current power consumption of an asset. How is that asset going to respond? Is it going to respond with a straight step change? Is it going to ramp down over a period of several minutes? What is it going to do? And then we can aggregate that up and figure out what our portfolio response might look like. And this could be a bit more involved than just doing a bit of time series analysis, because the response can depend on a lot of things. For example, in Foundries, it might depend on the day of the week, because they turn off on certain days of the week, or they have different operational parameters on certain days of the week. If it's HVAC or supermarket, this might depend on the outside or the inside temperature of the supermarket. There's a lot of different factors that come to bear here and that sort of need to enrich this model. So it's not just about looking at those points and saying, oh, well, we're just going to have a step change plus or minus something. There's really a lot of sort of enrichment in looking at different data sources that comes into it. And the first thing, we again, following our naive approach of doing absolutely everything in Nifi, we said, well, can we do this completely within Nifi? The answer is yes. Should you do it? Probably not. And again, it's sort of, I think all our flows sort of, when we started, looked at it like this, sort of extract properties, do some lookups, and do something with a Python script at the bottom. But hey, you know what? It did the trick. It actually worked. And this, again, took a little longer than half an hour to actually get the model working and all the lookups working. And there were a few more processors. That's not the complete thing. But the bottom line is you could actually do that. It was quite cool. And then at that point, we went, OK, now we need to make this a bit more sane. We need to see how we can integrate it with other tools. And that's when the power of Nifi and its extensibility really comes into its own right. So yeah, it's not very practical, not very easy to test or maintain. Testing was a big issue as well, because if you just have this running and somebody makes a change somewhere, because it's so easy to change, how do you know that it still works? And long, messy flows, well, I don't have to tell you, they're not easy to troubleshoot. So this was sort of our second approach. So in this approach, we use Nifi purely as an orchestrator, or distributor, as it were. So the messages come in to Nifi, and then maybe there's a bit of caching that happens or a bit of extraction of the properties of the message so that the downstream services don't need to care about how the messages are formatted. But then somewhere in the middle in that green box, a request is made to a service. So in our case, it's via HTTP because we have a proxy that abstracts all that machine learning stuff. And then it gets that response. Much simpler flow, a lot less responsibility. But at least this is Nifi doing what it's really good at, which is orchestrating stuff and then leaving the statistical and machine learning stuff to a system that's designed for that. So the first observation you might have is that in this case, well, why on earth are we even using Nifi? It seems you have a message coming in one end, you have a request being made at another. Well, you don't really need Nifi. It seems an overkill. You could use traditional stream processing. Storm, I'm pretty sure that wouldn't take very long to code up in Storm. Serverless, well, why not? We're using the Azure platform. We're using the Azure IoT Hub. We could probably write an Azure function that does all that. It doesn't require us to maintain any infrastructure. And the point is here that, first of all, that's not all we want to do. Second of all, when you go serverless like that, for instance, unless you want to add a lot of stuff to your serverless logic, you don't have that trail of data provenance. You don't know that, for example, this model made this change to the data and responded in this way, and that when the data was transformed, it was affected by a lookup that said that, in fact, the entity code was this, but it was actually incorrect. You don't have that. You don't have that lookup. So if something goes wrong later on, and you're relying on monitoring logs from Azure Functions, you're going to have a lot of trouble figuring out what it was. So maintainability is sort of a key concern here. And the other one is that, well, suppose you want to bolt other stuff onto it. And this is what I'm going to get onto now. Suppose you want to bolt on other stuff to it. Once you have this forecasting running, well, you want to validate it, right? You've already validated your model on historical data, say. But as data is coming in real time, suppose, for instance, you're dealing with a bitumen tank, and somebody changes the grade of bitumen in the tank. Now, when that happens, the tank will need to be heated to a different temperature. That's a fundamental shift in the state of that asset that you might not capture because the client's not going to tell you till the next morning, if you're lucky. So at that point, your model suddenly becomes invalid, and any forecast it makes is going to differ from reality by a very measurable and ever-increasing amount. So what you really want is a system that lets you compare what you're getting back from your model with reality. And then as time goes on, if those two things diverge enormously, then you know at that point your model is no longer valid. And then you can make a decision to go and refit the parameters. And it goes something like this. So you run a prediction, you have the forecast from your model. This forecast can be compared with an observable time series that you receive back from the device. And you can keep track, and because this is all sort of change of value data, we can do the very sort of compare points very easily. There's no need for like a lagged cross-correlation or anything to see where the series sort of intersect. And you can basically take a square error at every point in the time series, put that into a counter that you sort of increment over time, and then keep track of which counters are increasing faster than others. To say if this counter is increasing really, really quickly, then that means the model's obviously wrong. Quick, retrain it. And well, I'll tell you what we're thinking of doing with this after, but I mean, at the most naive level, you basically keep track of the counters, and then if a counter goes over a certain threshold, you refit the model. So, something like that. So you start off with a model that's fitted on historical data. You validate it. Hopefully, at that point, it's acceptable. You can generate a forecast, receive the data, observe difference with that data, increment the accumulated square error, and at that point, you can look if is this accumulated error acceptable or not. If it's not, then you retrain the model. That's very simple because acceptable errors might differ for different models. So at this point, we had sort of a global threshold, and we also had a sort of a scheduled retraining process. And it looked something like this. So again, this isn't the full flow. I've removed some stuff from it and sort of flattened it to make it fit on one slide. But this is using the distributed map cache to store the counters where the errors were being accumulated. And every time we got the model prediction, we would, every time we got a new reading, we would check that against the last cache model prediction, compute the difference, and then we would store that in another entry in the map cache, which we could then get and then pass it through, unfortunately, a tiny little script that would then compare and say whether this was over a threshold or not. And this is quite easy to implement. You can very quickly see what goes wrong, and you can very quickly observe as the data flows through what properties are changing in your flow file. And it also gives you as a free benefit that you can see the differential of this counter over time as a property, in your data provenance. Because for a given piece of data, every message that goes through here, one of the attributes that it'll have is that error. Even if it's not persisted at the other end, it's still stored within your data provenance. So something's going wrong for a period of time anyway, whatever the retention period of that is, you'll still have that information. So for us, the next step, we're going to move away from the distributed cache because it doesn't really admit some sort of like heap structure where we could do something more clever with the errors. So we're probably going to get that out of Nifi and I don't know, you use something slightly different for that. Maybe it could be, well, I'm not going to speculate, but it'll probably be something different that does have a data structure like a max heap. But we're still going to use Nifi as an orchestrator of all these different flows. And better reporting around all that, because at the moment we're relying on the Nifi GUI to do a lot of the internal reporting around this, which again kind of shows the power of Nifi really. Not that this is an architecture diagram or anything, but this is sort of what it looks like at the moment. So data comes in to the Azure IoT Hub, at which point we have a consumer that reads it, republishes it to Kafka. So on the right-hand side, we have Flink that we use for flows where we need more control over windowing and things like that, which aren't readily available. And Nifi, which isn't designed for that anyway. Everything goes through Nifi. We have this model registry that sort of associates models with different entities and different combinations of variables. It's just an HTTP proxy, usually between like a Jupyter notebook running a kernel gateway and the caller, so in this case, Apache Nifi. Actually, we're probably going to open source that soon, so you should check our GitHub page within the next month or so. So what it is basically a registry. So you can, with every observable you'd like to predict, you can associate a model for each entity. So it's designed for the IoT. So for each entity observable combination, you can associate a model, and a model can have different backends. So it could be either HTTP, it could be Azure machine learning, it could be IBM Watson service or whatever you want to use. But then they all come out in one interface, which is sort of a fit predict interface compatible with scikit-learn. Anyway, done with that tangent. So once it goes back through Nifi, it can then go through that whole sort of validation flow and then at some point get persisted. The sort of important thing to point out is that we're not, there's not a competition here between Nifi and Flink. They're fundamentally different things. Nifi is the orchestrator, and Flink is sort of is what we're using to do more, shall we say, processing stuff where we really need very fine-grained control, or a lot of code. I mean, if there's a lot of code going into any Nifi thing, for me, that's usually a code smelter. It should be moved somewhere else that's more suitable for dealing with it. Nifi is good at simpler things in that respect, even though it may be very composable. And so, from the point of view of our teams, this also has quite an impact because, so if you imagine in blue, you have our team of data scientists, and in the light gray, you have our team of software engineers. That sort of shows the breakdown of who's using what system. So our software engineers will tend to write more code in Flink because that deals with sort of data flows like aggregations, sort of windowed reporting, such as, over each 5-minute period, what was the maximal temperature of my bitumen tanks or something like that. And in blue, so you have data scientists who'll they'll be asking completely different questions. They might be trying to forecast quantities using their models that are shared with this gateway. They might be very simply trying to predict. So one of the latest things they've been trying to do is they've been looking at the throughput of a battery, which is essentially an arc length of power consumption. And that's something else you can do in Nifi very creatively, which we're probably going to move to Flink because that flow looks horrible as well now. But it introduces quite an interesting workflow as well, where Nifi becomes sort of the interface, where you have somebody who wants to compute some sort of data. So they just create a flow, they show that they can do it, and then at that point you make a decision and say, does this still look maintainable? Can we test this all right? Yes, is there too much logic living in scripts? All right, maybe we'll think about how we could re-engineer that and make better use of the ecosystem. But it's proven to us to be like a really good starting point. To get people who are not necessarily knowledgeable about stream processing or even about sort of hardcore software engineering in general, making them work at least at a proof of concept level. And I should point out that in this case, anything that gets persisted runs through Nifi as well. So you always have that sort of audit trail of every piece of data in your database. This is in case anybody mistook what I said for a sort of comparison or framework war between Nifi and Flink. It's not that at all. I love both of these tools. They just have very, very different purposes. Thank you very much for listening. I'm more than happy to take any questions. I think I've left plenty of time. I have left plenty of time for questions. So please feel free to ask anything. Yep.
Did you have any requirement for encryption, anonymizing data?
That wasn't our main concern because all the data coming in was secured already through SSL. So the communication within Nifi itself, or from Nifi to the backend services, uses HTTPS as well. So that communication was encrypted, and the connection to the database is also encrypted. You mean the connection within the cluster itself, right?
Yeah, a lot of the data processing. So encrypting the data before ingestion, and then perhaps decrypting it later on for the processing reasons or whatever.
Oh, right, I see. No. So the data that comes in to Nifi is not encrypted. It's encrypted in transit, but as soon as it hits Nifi, it's not encrypted. I do understand Nifi has really good capabilities for that, though. Any more questions? All right, well, thank you very much.